Hello, everybody, and welcome to this week's lesson. This week we are starting our algebra adventure. Today and over the next few weeks, we're going to be focusing on functions, which is one of the main topics in algebra that shows up on the GED test. So this week's lesson is functions and the coordinate plane. As we work through this lesson, you'll need pencil and paper, your welcome packet, and you might find a calculator useful as well. The calculator on your phone will do just fine. So our learning goals for this week, by the end of this week, you'll be able to use algebra related vocabulary to discuss math problems. Algebra really is sort of like the language of mathematics. It's this language that we use to describe patterns and relationships in the world around us. So I want you to feel confident using this special vocabulary when you are discussing math problems and thinking about these math problems. Next, you'll be able to evaluate exponents and roots of rational numbers, plot and identify points on the coordinate plane, identify a function in a table or graph as having exactly one output for each input. And our last learning goal is that you'll be able to write linear equations to represent context. Now that last one there, we're really just going to get a taste for that last skill this week. This last skill is something we're going to focus on in a lot more detail next week and the week after. So just getting a little bit of a start with equations and linear equations this week. Let's jump right in here. We're going to start off by talking about exponents and roots. So exponents and roots are another pair of operations that we can add to our list of operations that we already know. You want to remember that operations are the things that we do with numbers, right? So if it wasn't for our operations, math would just be a list of numbers sitting there, not doing anything. Operations are the actions that we get to take with our numbers. So we already know about addition and subtraction, multiplication and division, and now we've got exponents and roots. So let's talk first about exponents. Exponents are a way of showing repeated multiplication. So exponents are a way of writing repeated multiplication. Just like multiplication is a way of showing repeated addition. So exponents kind of build on top of what we already know. So repeated multiplication. So for example, let's say we have something that looks like this. So the way that you could read this, the way that you could say it to yourself or someone else, you could say 5 to the power of 2. You could say 5 to the second power. Or you could say 5 squared. This little 2 here, this is the actual exponent. So this is the exponent. And because exponents of 2 are so common, one of the more common exponents you'll see, they get their own special like little short name. So instead of saying an exponent of 2 or 5 to the power of 2, you can just say 5 squared. So that 2 is called an exponent. You might sometimes also see it called a power. I'm mainly going to call it an exponent though. And then the normal size number, the big number here, the 5, would be called the base. So what this is telling us to do, that exponent of 2 is telling us that we should take 2 5s and multiply them together. 5 times 5, which is 25. Okay, let's try another one. So let's say we have, 3 to the power of 3. So this is telling us to do 3 3s multiplied together. So 3 times 3 is 9, and 9 times 3 is 27. So 3 to the power of 3 is 27. Now, having an exponent of 3 is also a pretty common exponent, and so it has its own little special name. Just like an exponent of 2 means, you can say squared. When you have an exponent of 3, you can say cubed. So another way we could say this is 3 cubed equals 27. All right, let's try another one. Let's do 2 to the 4th power. So this is saying take 4 2's and multiply them together. So 2 times 2 is 4. 4 times 2 is 8. And 8 times 2 is 16. So 2 to the power of 4 is 16. Down at the bottom here in our operations table, I've got another example. So we've got 4 squared, which means 4 times 4, which is 16. So you can have an exponent that's any number. You could have 3 to the power of 100. You could have 3 to the power of -5. You could have 3 to the power of 1/3. You can have exponents that are any number, right? Just like you can add with any numbers, you can multiply with any numbers. You can also have exponents with any numbers. But for the most part on the GED, you're mostly going to see these smaller, simpler exponents like 2, 3, or 4. Okay, so let's talk about roots next. Now all of our operations, they come in pairs. They come in pairs of inverse or opposite operations. So inverse kind of has the same meaning as opposite. So for example, addition and subtraction are a pair of inverse operations. Subtraction kind of undoes the work that addition does and vice versa. So if you start with 2 and add 4 to it and then take away 4, you kind of end up back where you started. The one cancels out the other. Same thing with multiplication. If you start with 2 and then multiply by 4, but then you divide by 4, you end up back where you started at 2. So multiplication and division kind of cancel each other out. Same idea with exponents and roots. So roots are the inverse of exponents. They undo the work that exponents are doing. So I have an example for you here down at the bottom of the page in our operations table. 4, right, we said that 4 squared is equal to 16. That means if we take the square root of 16, it's going to be 4. So the square root of 16, you would ask yourself, what number squared equals 16? So what number times itself equals 16? Let's try some more examples with square roots, and then we'll talk a little bit more about other roots, right? Because just like you can have an exponent of 2, an exponent of 3, an exponent of 4, and so on, you can also have all different kinds of roots. Square roots are certainly the most common though, so let's start with those. What about the square root of 1? Well, you would ask yourself, what number squared equals 1? What number times itself equals 1? And that would be 1, right? 1 times 1 equals 1. What about the square root of 4? The square root of 4 is 2. What about the square root of 9? Well, 3 squared is 9, so that means the square root of 9 will be 3. Square root of 16, we said that was 4. About the square root of 25. The square root of 25 would be 5. Square root of 36. Well, 6 squared is 36. So the square root of 36 would be 6. We could keep going here. You might notice a pattern. I'm counting up here 1, 2, 3, 4, 5, 6. These numbers here, like 1, 4, 9, 16, 25, 36, these are all examples of perfect squares. Whoa. Perfect squares. A perfect square is a number whose square root is a whole number. And perfect squares are things that really just depend on your knowledge of your times tables, right? So if you know that 6 times 6 is 36, you should be able to figure out what the square root of 36 is. If you know that 5 times 5 is 25, you should be able to figure out that the square root of 25 is 5. So perfect squares are things that could show up on the non-calculator portion of the GED test. Again, they really just depend on your knowledge of your times tables. But what about numbers that aren't perfect squares? So let's say we wanted to know the square root of 30. Well, you would ask yourself, what number squared equals 30? Well, 5 squared is 25. 6 squared is 36. So it seems like it's going to end up being somewhere in between there, right? So the square root of 30 would fit right in between these two square roots here. And so we'd expect the answer to be right in between 5 and 6. We're going to get a decimal answer. So to do this, you would, to get the exact square root of 30, even though we know it's going to be 5 point something. It's going to be 5 plus a little decimal amount. To get that exact amount, you would use your calculator. So probably any calculator you're using will have a square root button on it. Exactly where it is and what it looks like will depend a little bit on your specific calculator. If you have a question about where your square root button is or how to use it, just get in touch with me and we can take a look at it together. But I'm using the TI-30XS calculator here. So this is what you use on the actual GED test. And on this calculator, the square root button is over on the side here. So I'm going to take the square root of 30, enter, and I get an answer of 5.477225575. I get this long decimal answer. And that's mostly what you're going to get when you're calculating square roots. You're going to get these long decimal answers. So I'm just going to round this off. I'm going to round this and say it's approximately 5.5, somewhere around there. So again, finding an exact square root like this is something you would do with a calculator. No one's going to ask you to do this in your head. It would take a very long time to figure out. But something that's a perfect square, as long as you know your times tables, should be a nice quick mental calculation for you. So another reason to be practicing your times tables if you aren't already. All right, so those are square roots. Like I said, those are the most common type of root that you'll see, and it's kind of the opposite of squaring something. Now you can also take other roots. You can take a cube root, which is the opposite of cubing something. You could take a fourth root, fifth root, and so on, right? You could take a 18th root if you wanted to. We're not going to do that, but you could if you really wanted to. So let's talk a little bit about cube roots. Now, like I said, these may show up on the GED math test when you are taking it, but probably they're not going to show up very much. So if you just want to stop at square roots, you feel good about that, that's fine. You can just stop there. But if you're feeling up for it, keep your ears open and we're going to go through cube roots. So let's return to thinking about exponents for a minute. 2 cubed, or 2 to the power of 3, right? That means 2 times 2 times 2, which is equal to 8. So if we were to take the cube root of 8, that means we're asking ourselves, what number to the power of 3, what number cubed is equal to 8? Now notice there's this little number here in the root. You can also do that with square roots. So technically a square root should look like this with the little 2. It's just that square roots are so common and they're kind of the default that we don't bother to write the little 2 there. We just assume that it's there. But once we get up into higher roots, we need to say what kind of root we're taking. So the cube root of 8, well, since 2 cubed is equal to 8, that means the cube root of 8 would be equal to 2. Let's try another one. So what about 5 cubed? Well, that means 5 times 5 times 5. 5 times 5 is 25, times 5 would be 125. So the cube root of 125 would be 5. All right, so let's get a little bit of extra practice here, just to make sure we got those basic exponents and roots down. So number 1, 5 squared. I would take a moment to pause the video, write down your answers to each of these questions, and then resume the video when you think you have the answers. So number 1, 5 squared. Well, that means 5 times 5, which is 25. You want to resist the temptation to treat it just like regular multiplication, right? This is not saying 5 times 2. This is saying 5 times itself. 5 times 5 is 25. So then the square root of 25 would be 5. 2 to the power of 3, or 2 cubed. Well, that means 2 times 2 times 2, which is 8. That means that the cube root of 8 would be 2. All right. So let's talk next about points on the coordinate plane. The coordinate plane is something we got a little taste of. Something we got a little taste of a couple weeks ago when we started talking about graphs. We talked about how bar graphs and line graphs, they have these two axes, a horizontal axis and a vertical axis, that show us like what are the two things we're comparing in the graph. So this is the same thing that we're talking about. The coordinate plane is also sometimes called the Cartesian plane. You might see that name used sometimes. That's named after the French philosopher and mathematician who developed this system. So the coordinate plane is a system for describing locations of points. It lets us say exactly where a point is. It is a two-dimensional surface. That's actually what plane, it's really what plane means. It means like a surface. So it's a flat surface with an x-axis and a y-axis. The axes, so that's plural of axis, the axes are number lines. And we've worked a lot with number lines over the last couple months. So these are two number lines that cross each other. And since they're lines, they extend forever in both directions. So right now up on the screen, I have a picture of a coordinate plane that goes out to +6 and -6, but you could keep going depending on what it is you're trying to show. These two number lines cross each other where each of the number lines is 0. So the center is 0 for both of our axes. And that crossing point, that 0 point, is called the origin. So it's kind of where both of these lines originate from. So to describe the location of a point on the coordinate plane, you do two things. First thing you do is you say where the point lies along the x-axis. You give the x coordinate. And you say where the point lies along the y-axis. You give the y coordinate. So that means every point, to give the specific location, it has two coordinates. The name of these two coordinates is the coordinate pair, right? It's two numbers, so it's a pair of coordinates. And the coordinate pair is always written like this, where you have parentheses and a comma separating the two numbers. The x coordinate always comes first, and then the y coordinate, it's in alphabetical order. So for example, the red point on this graph, well, the red point is lined up with +1 on the x-axis, so that's my x coordinate, and it's lined up with +2 on the y-axis, so that's my y coordinate. So we could say that this point is at the location 1, 2. We could even say this is point 1, 2. So let's get some practice with identifying coordinate pairs. Let's start with the yellow point in the middle here. Well, this point is at the origin, right? It's sitting at 0 on both the x-axis and the y-axis. So this would be point 0, 0. What about the red point? So the red point is lined up with 1 on the x-axis, and it's lined up with 3 on the y-axis. So that red point is located at 1, 3. And next we have this purple point. So the purple point is lined up with 2 on the x-axis and -1 on the y-axis. So it's at 2, -1. The blue point, well, the blue point is lined up with 0 on the x-axis, right? It's sitting right in the, like at the center of the x-axis. And then it's down at -2 on the y-axis. So the blue point is at 0, -2. And then finally, this green point is at -4 on the x and 5 on the y. So -4 and 5. All right, so next we're going to get some practice with plotting points. So plotting means like putting it on the graph. So our first point, we're calling it point A, is at 0, 5. So I'm going to be at 0 on the x-axis and then up at 5 on the y-axis. So this would be point A. Point B is at -2, 3. So I'm going to go over to -2 on the x and up to 3 at the y. So this would be point B. Point C is at 4, -1. So over to 4 and down to -1. Point C. Point D is at -5, -5. So over to -5 and down to -5. And finally, point E is at 1, 1. So over to 1, up to 1. Point E. So always keeping in mind when we are thinking about coordinate pairs that it's always x first and then y, right? It's going in alphabetical order. And the x will always be that horizontal axis. The y will always be the vertical axis. It's just sort of the tradition that we follow in math. Get back to my next slide here. Things got a little out of order. Okay, so like I said, these skills that we were just talking about are kind of leading us into our algebra unit or algebra topic. Algebra is a really huge topic in math. It encompasses a lot of different skills and ideas. It's also a very important subject for the GED math test. So the GED math test is made up of about 55% algebra related questions. So a little over half the test has to do with algebra. So that's why we're really going to spend a lot of time with this material. Like I said, algebra is a really big topic. And so there is a lot of different words that we're going to be using to describe what we're doing. And so I want to just get started by going over some of the words that are going to be coming up a lot in this lesson and over the next few weeks. So let's start by talking about variable. What does that word variable mean to you? Have you heard it used before, or a word that sounds kind of similar? Have you heard it used in math class, or have you heard it used outside of math class, just out in the world? So some things that I think of when I hear the word variable, I think of like, sometimes people will say things like, oh, the weather has been so variable lately. Or people sometimes say like variations, like, oh, there's lots of different variations of that thing. So in math, the word variable has kind of a similar meaning where it's talking about something that can change or something that comes in lots of different forms. So a variable is an unknown or changing quantity or number. So an unknown or changing amount. Usually, we have a variable, we write it using a letter, and usually it's a lowercase letter. Again, that's just kind of tradition. The letter is acting just as a placeholder for this unknown or changing amount. So another way you could think of a variable is it is a letter that represents a number. So it's just like a little placeholder. So let's say you work in a restaurant and each week your shifts change a little bit just depending on everyone else's schedule. You know, sometimes people call out sick and you have extra shifts or things slow down and you don't have as many hours. So let's say each week your hours change a little bit, but every week you work some amount. So we could come up with this variable H, let's call it H for hours. And we could say that H represents the number of hours that you work in a week. Just as an example. So the number of hours that you work in a week. So that's a variable. Let's talk next about expressions. So I'm going to start off by asking you the same question. Have you heard that word expression before? And what does it mean to you? Have you heard it in math class? Have you heard it outside of math class, just talking with folks in your regular life? So when I think of expression, I think of like people talk about facial expressions, right? Like what your face is showing. People might say like, oh, that's just an expression, right? So an expression can be like a little phrase that people just use. And in math, it kind of has the same meaning. So a mathematical or an algebraic expression is kind of just like a little mathematical phrase or a little mathematical like piece of a sentence. So an expression is a mathematical phrase that's made up of numbers, variables, and operations. So kind of the building blocks of our mathematical sentences. So expressions can be really simple. If you have 2 plus 3, that's an expression. Let's think about our example variable here, H, for the number of hours we work in a week. Let me ask you this. If you were going to, let's say you earn $15 an hour. You earn $15 an hour. How would you calculate your earnings for a week if you earn $15 an hour? Kind of ignoring taxes and all that stuff. Well, what you do is you would take 15 an hour and you'd multiply it times however many hours you worked in the week, right? So we could have this expression that represents how much money you made in a week. So this expression 15H, this is saying $15 an hour times the number of hours we worked in a week. When you see a number right next to a variable like this with nothing in between, that means multiplication. We just assume it's multiplication. So this is an expression that represents your earnings for the week. All right, let's talk next about equations. So equations are, an equation is just a statement that two things are equal or the same. So anytime you're using an equal sign, you're making an equation, basically. So an equation is two equal expressions. Two expressions that are equal. So you could have a very simple equation, like 2 plus 3 equals 5. Right, we're saying that this over here means the same thing as this over here. And let's say last week you earned $150. We could say that 15 an hour times the number of hours you worked ended up being equal to $150. So that's another example of an equation. And then you could actually solve this equation to figure out what that missing value is, that H. And equations can also get a little more complex than that. You could have something like x squared plus 4 equals y minus 2x, something like that. You get real crazy. But it's still just a statement that these two things are equal to one another. All right, let's talk next about relations. So a relation is a really general idea. Really the only reason I'm bringing up this word is because we're going to talk about functions, which are a type of relation. So I'm going to break a rule here of defining words. You're not really supposed to use the word in the definition, but I'm going to because I think it is like the clearest way to say it. So in math, a relation just means that you're talking about a relationship between two variables. So anytime you have some kind of relationship between things, that's a relation. So like the weather outside is related to the clothes that you choose to wear on a day, that's a relation. The number of hours that you work in a week are related to the amount of money that you earn. So here, this relation is describing how your hours are related to your earnings. So that's a relation. And in this lesson, we're going to be focusing on a special type of relation, which is called a function. So a function is a special type of relation. And the reason we're focusing on this special type in particular is that many relations are functions. So they're very common. They're also very useful when we go out and we try to describe relationships between things in the world. So for example, this example we were just talking about, this relationship between hours that you work and earnings that you make, that is a function. So a lot of the relationships that we encounter are the special kind of function. So let's talk about exactly what makes functions special. So a function is a special relationship between two variables, an input variable and an output variable. There are many different ways that we can show or describe or understand relations and functions. And we're going to practice with 4 different ways to do so. So we're going to practice showing functions verbally with words or descriptions. We're going to practice showing them algebraically with equations. We're going to practice showing them graphically or with pictures, and numerically with a list of values or numbers. So a function is a relation between input, so your input variable, and output variable, where each input has exactly one output. So that is the special characteristic that functions have to have. You put one thing in, you get one thing out. Let me give you an example of what I mean here. You might have a toaster in your kitchen. Even if you don't have a toaster, you probably know what a toaster is. It might look something kind of like this. There's my toaster. So think of this toaster as your function. A function is basically like a mathematical machine. It transforms things or performs actions. So what do you put into a toaster? Well, you put bread into a toaster, right? Hopefully. Maybe a Pop-Tart or something like that, but let's just stick with bread for now. So bread or something kind of like bread. So let's say you wake up in the morning and you put one piece of bread into your function toaster. That would be your input, right? That's what you're putting into the machine. What do you get out of your toaster after you wait for a few minutes? Well, hopefully, as long as everything's working correctly, you get toast, right? You'd put one piece of bread in and you would get one piece of toast out. So that would be your output. If you magically got 2 slices of toast out, that would be pretty remarkable, right? That would definitely be a morning that you would write about in your diary, something you would text your friends about. So if you put one piece of bread in, but you got 2 pieces of toast out, that would be a pretty magical toaster. And that would no longer be a function. So a function is a mathematical machine that follows this rule that where you put one thing in, you get one thing out, right? You're not magically turning one piece of bread into 2 pieces of toast. Not that that's bad if that happens, it just wouldn't be a function. Let me erase my magical toast here. So each input gets exactly one output. So that means that our function really kind of has 3 main components to it. We have the input, then we have the actual function or the action that we're taking, so what we are doing to transform the input, and then we have the output or what comes out at the end. So let's look at some examples of this. So let's remember that a variable is an unknown or a changing quantity, usually represented by a letter. And we said that a function is this special relationship between an input variable and an output variable. So your input variable can also be known as the independent variable. And it's often labeled with the letter X, not always, but X is kind of a traditional choice for the input variable. And then your output variable is also sometimes known as the dependent variable, and it's often labeled as y, again, just kind of for traditional reasons, or f of x. F of x is just shorthand for a function of x. Now, what we're talking here about input and output, or independent variables, dependent variables, this is a concept that is relevant also for the science GED test. That test will also have some questions usually about independent variables and dependent variables. So you might be learning about those also in your language arts and science and social studies class. So we've got our input variable and our output variable. Remember, you put your bread in, and then what you get out depends on the bread that you put in, right? So that's why the output is also called the dependent variable. It depends on what gets put in. So for example, let's return to thinking about like dollars and hours worked and our total earnings. So Robin earns $15 per hour. The equation below represents her total earnings based on the number of hours she works. So here we have an equation that represents a relationship between input, so the number of hours that she puts into her job, and output, the amount of money that she gets out of her job, right? So this equation is saying that her earnings, her total earnings, are equal to 15 an hour times the number of hours that she works. So this right here is an example of a function. It is actually a linear function, which we're going to be talking more about next week and the week after that. So we said that this thing here, right, is an equation that's representing this relationship between earnings and hours, right? So this equation is showing us a function. An equation is just a mathematical statement that two things are equal to each other. So we've seen like a verbal description of this relationship between hours and earnings, right? So we've seen a verbal description with words. We've seen an algebraic representation, right? So an equation representation, but we can also have a graphical representation and a numerical representation. Right, these are the four different ways to represent functions that we have. So let's first talk about this graphical representation. If you take a look at the x-axis of this graph, so the horizontal axis, what are those numbers representing? So we see 1, 2, 3, 4, 5, 6, 7, 8. What do those numbers mean? Well, in this context, for this specific function, those numbers are the hours that Robin is working. And then the vertical axis, the y-axis, is showing her earnings, or the number of dollars that she's getting. So this red line that's kind of sloping upwards, is a visual way of showing the relationship between the number of hours that she works and the number of dollars that she earns. So if she works 0 hours, she gets $0. Right? That's the way the world works. If she works for 1 hour, she gets $15, and so on, right? So 2 hours is $30. She could work 2.5 hours, and she would get $37.50. 3 hours, 4 hours, right? So this red line is a visual representation of this relationship between hours and earnings. And we could keep going up from here. Our graph just has to stop at some point, right? And then the numerical representation, the table or list of values, is really showing us the same information. It's giving us some example input output pairs from this relationship. So you put 0 hours in, you get 0 hours out. 1 hour in, $15 out. 2 hours in, $30 out, and so on. Right, we just picked the inputs 0, 1, 2, 3, and 4 here, but depending on the situation, you could pick different inputs. So I could say, well, what if she works for 40 hours in a week? How much would she earn? Well, it would be 40 times 15. It would be $600 if she worked for 40 hours. I'm probably not going to put negative numbers there because in this situation, negative numbers don't really make sense, right? What are negative hours that you worked? Doesn't really mean anything. Okay, so the next or the last thing that we are going to practice today is we're going to practice identifying a function. We're going to do it two ways. We're going to do it when looking at a table first, and then the second way is we're going to do it while looking at a graph. So let's start with tables. To identify functions, to determine whether or not something is or is not a function, we need to remember what a function is. We need to remember the definition of a function. So we want to remember that a function is a special type of relation where there is exactly one output for each input, right? You put one piece of bread in your toaster, you get one piece of bread out. You don't get two pieces of toast out. So let's start with this first table here. If I put -2 into my function toaster, I'm only seeing an output of -4. If I scroll down the rest of my table here, I'm not seeing -2 paired with any other output. Same thing with -1. It's only giving me an output of -2. 0 is only giving me an output of 0, and 1 is only giving me an output of 2. So this first table is a function. It meets that definition where each input is only giving you one output. Let's look at the second table here. So I look at all my inputs. There's actually only one input here, an input of -2. This one input is giving me 4 different outputs. So it's like I'm putting one piece of bread into my toaster and I'm getting 4 pieces of bread out. That is a magical toaster. That is not a function. It's still a relation, right? There's still some relationship here between X and Y. It's not that it's wrong or bad. It just doesn't happen to be a function. All right, third table here. I look down my list of input values. I see 1 with 3, 4.75 with 6.75, -2 with 0, and then 1 again. You might be thinking, oh no, 1 is gonna get 2 different outputs. However, it's actually going with the same value both times, right? So both times 1 is giving us an output of 3. That's fine, we can repeat the same thing. Notice also here that we have some decimal numbers. That's totally fine as well. For the most part, we've used whole numbers so far just to make it a little easier on you. But you can have functions involving any numbers. You can have negative numbers, fractions, decimals, mixed numbers, really big numbers, really tiny numbers, whatever. So number 3 is an example of something that is a function. Now let's look at the fourth table here. So it looks pretty similar to the third table. I see 1, 4.75, -2, and 1. There's only one difference here. And that's that the input of 1, now it's giving me 2 different outputs, right? So this one input, this one piece of bread is giving me 2 different pieces of toast. It's giving me a 3 and a -1. That is a problem in terms of it being a function. So number 4 is not a function. So this is an example of one type of function related question that you might encounter on the GED test, where you are asked to decide whether or not something is a function. All right, so let's get some more practice with this. I'd like you to take a moment to look at these four relations. And for each one, I want you to tell me, is it a function or is it not a function? So pause the video and try these four problems. And when you are done, return to the video and we're going to go through them together. So number one, looking at that numerical representation, is this a function or is it not a function? Well, when I look down at my inputs, I see each input there is unique, right? Each one, there's no repeats there. That kind of right away tells me that this is going to be showing a function because each input is only going to have one output. So number one is a function. Each input only has one output. What about number two? So -5 goes with -5, -4 goes with -4, -3, -3, -2, -2, 6 goes with -5. This also is a function. Now you might have been thrown off because two inputs, -5 and 6, are both giving you the same output. That's fine, right? That actually doesn't really have much to do with whether or not something's a function. What we look at is we look at each input. So this input of -5, it should only have one output. The input of -4 should only have one output. It shouldn't show up with any other numbers. -3 should only have one output. -2, only one output, and 6, only one output. And this, right, that's what's happening here. There, each input is only showing one output, right? You're putting one piece of bread in, you're getting one piece of toast out. You're not getting multiple pieces of toast. Some of your pieces of toast look the same. That's okay. You're only getting one piece of toast per piece of bread. All right, third problem here. So this is definitely not a function. The input of 0 has two different outputs. The input of 1 has two different outputs. So this is not a function. And finally, number 4 is, it's not a table, but it's still giving us a list of input-output pairs, right? So a list of XY pairs or coordinate pairs, as we talked about before, right? So this is X, Y, X, Y, and so on. So look at your X's, 0, -1, -2, -3, and 8. Do each of those X's have one output? And yes, they do. One way you can quickly determine that is that each X, each input value only shows up once. There's no repeats in the X's. So number 4 also is a function. All right. Now on to our last type of problem for today. So this is where we're going to practice identifying a function using a graph. So instead of looking at a table, looking at a graph. And to do that, we use the vertical line test, which is a quick visual check that we can do to see if a graph is showing a function. Now, the vertical line test is still based on the idea of having one output for each input. If we think for a moment, let's think about a table of values here. So I'm going to have X, Y, and let's say I have an input of 3 and an output of 1, an input of 3 and an output of 2, an input of 3 and an output of 3. Is this a function or is this not a function? This would be not a function, right? Because one input is giving you multiple outputs. One piece of bread is giving you multiple pieces of toast. So this would be not a function. Now let's graph this on one of these graphs here and see what it looks like visually. So this is saying the point 3, 1, 3, 2, and 3, 3. So when something is not a function, what happens is you get points or pieces of the function that are lined up vertically. They're stacked one on top of the other. They're exactly on top of each other. So that's where the vertical line test comes in. The vertical line test says that if you draw a line through a graph, draw a vertical line through anywhere on a graph, you should only cross the graph once each time. If you cross it more than once, so if it intersects more than one point, it fails the vertical line test and it is not a function. So you can see here with these 3 red dots, when I draw a vertical line through it, it intersects, it crosses each of those dots. So it's crossing this 3 times. So that means it's not a function. But let's try this actual graph here. So this blue curve that we see. Remember, the axes are not actually part of the function. That's just part of the labels that we're using. What we're interested in here is this blue curve. Now imagine drawing vertical lines all along this curve. I see that anywhere I draw a vertical line, even on the edges here where it looks like maybe it's getting a little bit vertical, but it's still not quite vertical. The curve is still like curving away to the side a little bit. So anywhere I draw a vertical line through this blue curve, my vertical lines will only ever touch the curve at one point. So this first graph passes the vertical line test. It is a function. What about the second graph here? If I draw a vertical line anywhere along this blue line, those vertical lines will only ever cross at a single point. So this passes the vertical line test. It is a function. Since it's a straight line, we'd actually call it a linear function. And then the third graph here, if I start drawing vertical lines through the graph, I'll see my vertical lines are crossing at 2 points. They're not crossing at 1 point. I can see that there's parts of this graph that are like stacked. They line up vertically. They're one on top of another. So this graph fails the vertical line test. It is not a function. And that's the vertical line test. So let's get a little more practice with that. Graph A, kind of imagine drawing some vertical lines. And you can actually even use the grid lines that are already on these graphs. You can kind of use those as your vertical lines. You can see that a vertical line is only ever going to cross this graph at a single point, even though it gets like pretty steep at the ends here, pretty steep at either end, it's still sort of curving to the side slightly. On the GED test, if you're given problems like this, it will always be like an obvious pass or an obvious fail. If you have something like this curve where you might be thinking like, oh, that looks kind of vertical, probably it's not. So if it's vertical, it means it has to be exactly straight up and down. If it's curving off to the side a little bit, that's not vertical. So it's still going to pass the vertical line test. So graph A is a function. What about graph B? Anywhere I draw a vertical line through this thing, only going to cross once. So graph B, also a function. And finally, graph C. If I draw a vertical line through this circle, my vertical lines are going to be crossing at more than 1 point. So this circle is not a function. Doesn't mean it's bad or wrong, just means it's not a function. So circles are not functions. Okay. So we're going to wrap up today with 3 more practice problems that are similar to the types of problems that you might see on the GED math test, similar to what we just talked about. So number 1, without repeating one of the existing coordinate pairs in this table, select 2 numbers that would make the following a function. So I've got this table here. When I look at this table, it is already showing a function. So when I look down the inputs, each input is unique. And so it's only going to have, each one's only going to have one output. So it's already showing me a function. I want to pick from this list of numbers. I want to come up with a pair of numbers that I could add to this table that would keep it a function. So there's lots of different correct answers to this problem. I'll give you a few correct answers. You could have you could actually choose 6 and 4. Right? If you put 6 and 4 down at the bottom here, that would be fine because 6 goes with 4 in this function. You could choose 3 and any of the numbers because none of those x's are 3. So you could choose 3 and 1, or you could choose 3 and 5, or 3 and 3, or 3 and 6. You could choose 5 and 3 because that pair is already in the table here. So those are a few examples of correct answers to this problem. If you have an answer written down, you're not sure whether or not it's correct, you can always send me a message and I will talk about it with you. All right, determine whether tables A, B, and C represent functions. So the similar type of questions here. We're still looking at tables, thinking about whether or not they're functions. Table A. I want you to notice here actually that the input and output variables have different labels. So A, we've got an input M, output N, input P, output Q, input T, output S. Again, like I said, you don't have to use X and Y or X and F of X. It's just sort of traditional, but you really can use any letters you want. You would always assume that the first column is showing you the input. So no matter what it's called, unless it's called output, you can just assume that it is the input. So table A, looking at table A, that looks like a function to me. The only thing that I would double check is this 3 that shows up twice, but both times it's giving the same output. So that is fine. That means this is a function. Table B. I look down my list of inputs here. Each input is only showing up once. None of them are repeated. So I know right away that each input is only giving me one output. So this is a function. And it's fine that they are all giving an output of 5. Not a problem. It's just that each input is only giving one output. So 1 only gives you 5. It doesn't give you any other number. 2 only gives you 5. Doesn't give you any other number. And so on down the list here. All right, now we get to table C. Now this is where we run into some trouble. Here we've got one input, one piece of bread that is giving us 5 different outputs. One piece of bread is transforming into 5 different pieces of toast. It's a magical toaster. So this would not be a function. It is a relation between input and output, but it is not a special function. Okay, and our final problem here is number 3, identify which of the following graphs represent functions. Well, let me label them here. Let's call this A, B, C, and D. So you want to determine which of these are functions. All right, well, we do the vertical line test, right? I draw a vertical line here through A. This vertical line is completely overlapping with the side of that triangle. So that's a problem, right? It's overlapping at many, many points there, infinitely many points actually. If I draw other vertical lines through here, I run into problems. Again, it's intersecting twice. So this definitely fails the vertical line test. It is not a function. B, when I go through and if I draw some vertical lines through it, that's totally fine. B is a function. Same thing with C. I can draw vertical lines all along this curve. Those vertical lines only ever cross the curve at one point. So C also is a function. Now D is actually the same curve, just rotated 90 degrees. When I draw a vertical line this time, it's crossing the graph at many points. It's crossing at 4 different points. So this fails that vertical line test. It is not a function. All right, everybody. Well, thank you so much for joining me on this lesson. Your homework for this week, your Worksheet Wednesday assignment, will be focusing on evaluating exponents and roots, plotting points on the coordinate plane, and identifying functions using tables and graphs. So if you do have any questions, please let me know. Make sure you are reading all of the posts on the Google Classroom this week. I hope you are having a great day, and I will talk to you all again very soon.